a door 2.3 meters high and 1.3 meters wide has a mass of 13 kilogram. And in this case, we are supposed to determine the horizontal and vertical force components exerted by each hinge on the door. As you see, each hinge is here, two hinges, and the position of actually the hinges are symmetrically positioned on the door because this one is 0.4 meters below the top of the door and the other one is 0.4 meters above the bottom of the door. So, and the door also has a regular geometrical shape. Therefore, the mass, which is the center of mass, will be in the middle of this door, and also the gravitational force will be acted on the middle, directly on the middle of the door towards down. This will be mg. So we need to first identify which forces are acting on the door from each hinge, from the hinge on the door. Okay. So we know that these two hinges, they need to act a vertical upward force on the door to keep it in a balanced position. Let's call this hinge the top one number 1, okay, and the other one hinge number 2. Let me write this one a little bit above. Okay, hinge number 1, hinge number 2. So we know these two, but they also exert a horizontal force on the door, and how to find that is it's very easy, because suppose like we remove hinge number 2, then the door tends to rotate, yeah, around this direction. To keep this balance, hinge number 1 must exert a force towards this direction, and also hinge number 2 must push the door outward towards this direction. Okay, so we need to label these forces also, because this is hinge number 1. So I will call the horizontal one, I will label it as fx1 and fy1, because this is towards x-axis, and the other one, vertical one, towards y-axis. Similarly, the same thing to hinge number 2, fy2 and fx2. Now we need to consider this case, as we see is a third condition equilibrium. Is the combination of first and second condition of equilibrium. So we know that the first condition of equilibrium, we have two equations. Sigma fx must be equal to 0 and sigma fy must be equal to 0. And the second condition of equilibrium states that sigma moment of force must be equal to 0, or torque must be equal to 0, the sum of moment of forces acting upon the hinge. So we will start by second condition of equilibrium. We will start by calculating this one, to calculate the moments of forces, but we need to choose a fulcrum or pivot, because we know that moments of force or turning effects must be with respect to a fulcrum. We choose hinge number 2 as the fulcrum. We choose hinge number 2 as the fulcrum, and we will find out the forces that make turning effect with respect to this fulcrum. So one is fx1. fx1, if you notice fx1, there is a distance between fx1 and fulcrum. Here is the fulcrum. And there is a distance here, and as you see, we are dealing with this case, fx1, and here is the fulcrum. So there is a distance, and as you see, the force is perpendicular to the distance, therefore it will definitely create a moment of force or a turning effect or a torque. But we need to find out this distance. We have got the height of the door, and we see in each side 40 centimeter or 0.4 meters we need to deduct from both sides. So doing that, we will get this distance 1.5 meters, which is D or R. And we see this will create a clockwise turning effect or moment of force or a torque. Okay, so the turning effect will be moment clockwise moment like that will be equal to 1.5 meters times fx1. But the second force that creates a torque or makes a turning effect is mg, the weight of the door. We see the fulcrum is hinge number 2, and so there is a distance between the fulcrum and the mg. So to calculate this distance, we have the width, we need to divide it by 2, and we will get like such a case. We have a force mg, and there is a distance between this mg and fulcrum, which is 1.3 meters divided by 2, which will give us 0.65 meters. So this will create a counterclockwise moment. So therefore it will be counterclockwise moment, and the magnitude will be 0.65 0.65 meters mg. Okay, now the sum of this turning effects must be equal to 0. So we say sigma m is equal to 0, the second condition of equilibrium. We replace them with numbers, and we say counterclockwise positive and clockwise negative. We assign that. So we say 0.65 mg plus 1.5, and this is meters, fx1 must be, this is negative, must be equal to 0. Okay, and substituting m, which is the mass by with 13 kilograms, and g, we take it 10, almost 9.8 or 10, we will get fx1 with a magnitude of 56.3 newtons. So this is fx1, the horizontal component of the force acting by the hinge on the door. Okay, now we will use the second condition of equilibrium, the first condition of equilibrium, which is sigma fx is equal to 0 to calculate fx2. So therefore, those forces heading to the left negative, those forces heading to the right positive. We assign them positive. So therefore it will be negative fx2 plus fx1, which is equal to 0. Then we will conclude that fx1 must be equal to fx2. Therefore, fx2 also is equal to 56.3 newtons. Okay. Then we also need to use sigma fy is equal to 0, and then we need to take into consideration the all forces towards vertical axis or y-axis. Those forces heading down or towards down negative, those forces heading up positive, assign them positive sign. So therefore it will be minus mg plus fy1 plus fy2 must be equal to 0 to keep the door balanced. Therefore, fy1 plus fy2 is equal to mg. And looking at the case carefully, we will realize, based on the symmetrical position of the hinges, and also because the door is has a regular geometrical shape, we can say that these forces are equal. So we can say fy1 is equal to fy2, which is equal to fy. Therefore 2fy is equal to mg, and fy is equal to, we replace them with numbers, we plug in the numbers into the equation, and then we will get 113 Newton divided by 2, which is equal to 65 Newton